Assalamualaikum and hi again. This video is on the last parameter we will learn in chapter 3 on estimation. We will explore the technique to estimate the ratio of two unknown population variances denoted by sigma 1 squared over sigma 2 squared, and hence for the ratio of two unknown population standard deviations sigma 1 over sigma 2. Are you ready? Let's go. 3 learning objectives for this topic. What are they? Let's look at the 3 learning objectives. At the end of this session, you should be able to achieve the 3 objectives. The first learning objective is you should be able to identify or calculate a point estimate for the ratio of two unknown population variances, sigma 1 squared over sigma 2 squared, and hence for the ratio of two unknown population standard deviations, sigma 1 over sigma 2. The second learning objective is you should be able to construct a confidence interval for the ratio of sigma 1 squared to sigma 2 squared, and hence for the ratio of sigma 1 to sigma 2, or vice versa if you're talking about sigma 2 squared over sigma 1 squared, and hence for sigma 2 over sigma 1. And finally, you should be able to interpret the constructed confidence interval for the ratio of two population variances, and hence for the ratio of two population standard deviations. Before we go into detail on the contents of this topic, let us be familiar first on an F distribution and how are we going to find an F score from a statistical table booklet. First, what is an F distribution? If we have two independent chi-square random variables with degrees of freedom nu1 and nu2 respectively, then the ratio of these two independent chi-square variables, each divided by their respective degrees of freedom, is said to have an F distribution with nu1 and nu2 degrees of freedom. Here, nu1 is given as the first sample size n1 minus 1, and likewise nu2 is the second sample size n2 minus 1. As we know from the topic on estimating a single variance, the chi-square variable is always positive, so the ratio of the two chi-square will also be positive, right? In addition, as chi-square distribution is rightly skewed, we should expect that the distribution of the ratio of two chi-square random variables will also be rightly skewed. Therefore, a possible answer of an F distribution looks like this. Obviously, it's not symmetrical and it is skewed to the right. The values of F start from 0 and obviously are always positive. Now, how can you find an F score from the statistical table booklet that we are using currently in the class? The table provides values of F in such a way that the probability of a random variable F being at least F alpha nu1 nu2 is alpha, given by the red shaded region, and F alpha nu1 nu2 is located here in this figure. You can observe from the figure that the bigger the red shaded region is, that is, the bigger the alpha value is, the smaller you should expect the value of F alpha nu1 nu2 would be as it comes closer to 0. The current statistical table gives you values of F alpha nu1 nu2 for a limited choice of alpha values, which include 0.001, 0.01, 0.025, 0.05, and 0.1 only in pages 38 until 47. What if alpha is equal to 0.95? It is not available in the stat table. But don't worry, you can still work out its value by using this equation. F1 minus alpha nu1 nu2 is 1 over F alpha nu2 nu1. Notice that we can use F score at alpha in the denominator. However, its degrees of freedom are now nu2 first, followed by nu1. Let us now look at a number of examples on finding the F scores from the stat table booklet in the next page. We continue in this slide to find a number of F scores. In doing so, please refer to Table 7, pages 38 until 47 of the latest statistical tables booklet. Values of F scores are given for only 5 choices of alpha values, as mentioned in the previous slide. For example, when alpha equal to 0.001, you can find the F scores in pages 38 and 39. When alpha equal to 0.01, the F scores are in pages 40 and 41, and so on. Other values of alpha available in the table are 0.025, 0.05, and 0.1. Now, how do we read the values of F alpha nu1 nu2 from the table? Okay, for any alpha value, what you need to do first is to read the nu1 value vertically from the first column, and next go horizontally until you get to the nu2 value that you want. Eventually then you will get the F score that you are interested in. Let's try these examples. Identify the value of F 0.001129 from the table. So what do you have to do? First, go to alpha equal to 0.001. That is in page 38. Next, find nu1 equal to 12 from the first column. Once you get to 12, go horizontally until you get to nu2 equal to 9. You will notice the corresponding F 0.001129 is 9.57. Do you get the value? Okay, good. Let's try another example. What about F 0.011520? Here, you need to turn to page 40 and 41 for alpha equal to 0.01, not for alpha equal to 0.001 this time. So be careful. Now alpha is 0.01. Repeat the same steps as before. Look first at nu1 equal to 15 from the first column, And next, move horizontally to new 2 equal to 20. This is in page 41. Do you get 3.09? If you do, that's very good. You can repeat the same procedure for the next F-score, F0.05, 18, 16. Here you need to go to pages 44 and 45 for alpha equal to 0.05. What do you think the value of F0.05, 18, 16? If you get the value 2.30, then again you are on the right track. Well done. Next question. How to find F 0.99 2015? Of course, alpha equal to 0.99 is not provided in the table. But we know alpha equal to 1 minus 0.99, which is 0.01, is there in the table, isn't it? Therefore, we can use the formula F 0.99 2015 equal to 1 divided by F 0.01 1520. Where F 0.01 1520 was 3.09 that we found earlier. By dividing 1 by F 0.01 1520, which was 3.09, then you get the answer for F 0.99 2015, which is around 0.3236. Can you follow me? Very well then. Now, what about the last example? Can you calculate F 0.975 10 13? Here again, by formula, F 0.975 10 13 is the inverse of F 0.025 13 10, right? Please notice the positions of new 1 and new 2. You can find F 0.025 1310 from page 42, which gives a value of 3.58. Therefore, F 0.975 1013 is simply 1 divided by 3.58, which gives us a value of around 0.2793. Hopefully you get the idea how to get the value of F alpha nu 1, nu 2 from the table. Suppose we have two normal populations with variances sigma 1 squared and sigma 2 squared respectively. Assume that the values of these two variances are unknown. If we take a random sample from every population, we can calculate sample variances from each sample to estimate the unknown population variances respectively. That is, the first sample variance, which is S1 squared, can be used as a point estimate for sigma 1 squared, while the second sample variance, S2 squared, can be used as a point estimate for the second unknown population variance, which is sigma 2 squared. If we want to compare the variability existing in the two populations, we can look at the ratio of the two population variances. However, since the population variances are unknown, how are we going to estimate the ratio of these two unknown population variances? That is, what is a point estimate for the ratio of sigma 1 squared to sigma 2 squared? And hence, what is the point estimate for the ratio of two unknown population standard deviations, sigma 1 to sigma 2? The answer for the first part is we can use the ratio of two sample variances, S1 squared to S2 squared, as a point estimate for the ratio of two unknown population variances, sigma 1 squared to sigma 2 squared. Taking a square root of this ratio, we can then find a point estimate for the ratio of sigma 1 to sigma 2 given by the ratio of the first sample standard deviation S1 to the second sample standard deviation S2. We will look at an example on the point estimates for the ratio of population variances and for the ratio of population standard deviations. Please refer to example 3.6 in Statistics for Engineers textbook, page 75. A quality engineer is studying the diameter of stainless steel rod manufactured on two different machines. Two random samples of 16 and 13 rods respectively were selected, which gives the variances of diameter values 0.3 cm squared and 0.4 cm squared respectively. Assume that the data were drawn from two independent normal distributions. The first question in this slide is, what is the point estimate for the ratio of population variances of the diameters? If we look at the given sample information again, we can notice that the value of S1 squared, which is the first sample variance, is given by 0.3 cm squared, and the value of S2 squared, which is the second sample variance, is given by 0.4 cm squared. Using this sample information, we can then get the point estimate for the ratio of two unknown population variances of the diameters given by the ratio of two sample variances of the diameters from the samples, that is 0.3 divided by 0.4, which gives us the answer equal to 0.75. Please do not square 0.3 and 0.4 because these two values are already the values of sample variances. Having solved the first question, next, what is the point estimate for the ratio of population standard deviations of the diameters? What can we do here? Alright, as you know, the standard deviation is just the square root of the variance. So in this case, what we can do is to take the square root of the first answer, that is square root of 0.75, which gives us a value around 0.8660. So this is the point estimate for the ratio of sigma 1 to sigma 2. Now, what can you infer from both answers? Notice that both ratios are less than 1, isn't it? We can consider 1 as a reference value to recognize if the first variance is estimated to be larger or smaller than the second variance. In this example, you may conclude that based on the sample data, the variability of diameters of the rods produced by the first machine is estimated to be lower than the variability of the diameters of rods produced by the second machine, since the ratios are both smaller than 1. Let us now proceed with constructing a confidence interval for the ratio of two unknown population variances sigma 1 squared over sigma 2 squared. A two-sided 100 times 1 minus alpha percent confidence interval for sigma 1 squared over sigma 2 squared is given by this expression. We can clearly notice that the point estimate of sigma 1 squared over sigma 2 squared, which is s1 squared over s2 squared, are in the numerators for the lower and upper limits of the confidence interval. We can also see that the denominators in both lower and upper limits of the interval are the f-scores, where we use f alpha over 2 nu1 nu2 in the lower limit, and we use f1 minus alpha over 2 nu1 nu2 in the upper limit. As we know from the previous slide, not all f-scores are available in the stat table. Therefore, an alternative expression for the confidence interval that we can use is as follows. Notice that the lower limit, previously written as s1 squared over s2 squared divided by f alpha over 2 nu1 nu2, is now s1 squared over s2 squared times 1 over f alpha over 2 nu1 nu2. For the upper limit, the denominator f1 minus alpha over 2 nu1 nu2 score is not available in the stats table. Therefore, we can replace it with 1 over f alpha over 2 nu2 nu1. Replacing this expression in the upper limit of the confidence interval, we then get the upper limit to be s1 squared over s2 squared times f alpha over 2 nu2 nu1. In short, the two-sided 100 times 1 minus alpha percent confidence interval for sigma 1 squared over sigma 2 squared is s1 squared over s2 squared times 1 over f alpha over 2 nu1 nu2 and s1 squared over s2 squared times f alpha over 2 nu2 nu1. Please make sure the order of the degrees of freedom are correct. For the lower limit, you have nu1 nu2, whereas for the upper limit, you have nu2 nu1. A number of points to note here is that first, nu1 is n1 minus 1, where n1 is the first sample size, whereas nu2 is n2 minus 1, where n2 is the second sample size. Second, the values of f-scores can be obtained from table 7, pages 38 till 47 from the new or current statistical tables booklet. And finally, which is very important, please do not use a plus-minus sign in the confidence interval formula, as we use an underlying f-distribution in constructing the confidence interval, where f-distribution is not symmetrical about 0, so no plus-minus sign in the confidence interval formula. In addition, the values of both lower and upper limits of the confidence interval can never be negative, as we have ratio of variances, where variances measure variability And as you know, variability can never be negative. Having constructed a two-sided 100 times 1 minus alpha % confidence interval for the ratio of two unknown population variances, we can then obtain a two-sided confidence interval for the ratio of two unknown population standard deviations at the same degrees of confidence, given by this expression. The confidence interval for the ratio of sigma 1 to sigma 2 is the square root of the lower and upper limits of the confidence interval for the ratio of two population variances. Here, the lower limit is the square root of S1 squared over S2 squared multiplied by 1 over F alpha over 2 nu1 nu2, whereas the upper limit is the square root of S1 squared over S2 squared multiplied by F alpha over 2 nu2 nu1. Let's now look at an example on constructing a confidence interval for the ratio of two unknown population variances and standard deviations in the next slide. Let's look at an example on constructing a confidence interval for the ratio of two population variances and standard deviations. Please refer to task 3.11 in page 76 of Statistics for Engineers textbook. An engineer is studying an axial load of aluminium cans. It is measured using a plate where an increasing pressure is applied on top of the can until it collapses. The maximum weight the sides of the can support is the axial load. Two random samples of sizes 10 and 7 were selected randomly, and the standard deviations of the axial load were 10.1 kilograms and 11.8 kilograms respectively. Assume the axial loads are normally distributed. The question we want to address in this slide is find a 90% confidence interval for the ratio of the population standard deviations of the axial loads. So how are we going to find this 90% confidence interval based on sample information? In answering this question, we need to know the sample sizes and the sample standard deviations besides the two F-scores for the lower and upper limits. The sample information provides us with sample sizes, which are N1 equal to 10 and N2 equal to 7, whereas the sample standard deviations are given by S1 equal to 10.1 kilograms and S2 given by 11.8 kilograms. Having identified or recognized all this sample information, we can now solve the question in the next slide. We continue with the solution for task 3.11 in this slide. After recognizing all information required to construct the confidence interval and write the information using correct notations, we can now find the answer. The information required can be written like this. From samples 1 and 2, we've identified the corresponding sample sizes N1 and N2, and the sample standard deviations S1 and S2. We only have one case in constructing the confidence interval for the ratio of population variances or for the ratio of population standard deviations, that is, to use an F distribution. In order to construct the confidence interval for the ratio of the standard deviations, Like in this example, we can first construct the confidence interval for the ratio of variances. Here, the 90% confidence interval for sigma 1 squared over sigma 2 squared is given by this formula. From Table 7, page 44, F 0.0596 is given by 4.10, and that is the value for the lower limit, whereas F 0.0569 in the upper limit is given by 3.37. Do you follow me? Very good. Now substituting all these relevant values required in the formula and doing a simple calculation, the 90% confidence interval for the ratio of population variances sigma 1 squared over sigma 2 squared is then given by 0.1787 and 2.4689, which are correct to 4 decimal places. Please do not stop here. In this video, we are interested in the confidence interval for the ratio of two population standard deviations. Therefore, we need to go further to the next step, that is, to take the square root of these limits. Therefore, the 90% confidence interval for sigma 1 over sigma 2, which is the ratio of two population standard deviations, is the square root of 0.1787 and the square root of 2.4689, which gives us the final answer, that is 0.4227 and 1.5713. We still continue with task 3.11 in this slide. Suppose we have this extra question. Based on the constructed 90% confidence interval for the ratio of population variances or the population standard deviations, could there be any difference between the population variances or between the population standard deviations of the cans axial loads? In other words, could there be any difference in the variability of axial loads of cans measured from different groups or populations? How to verify the answer? The answer to this question is no difference. There could be no difference between the population variances or between standard deviations of the cans axial loads. How to verify? If you notice, both confidence intervals, that is the confidence interval for the ratio of variances and for the ratio of standard deviations, contain a lower limit which is less than 1 and the upper limit which is more than 1. This indicates that the confidence interval contains a ratio of 1. When the ratio is 1, it implies that sigma 1 squared is equal to sigma 2 squared, or sigma 1 is equal to sigma 2. Therefore, we can take a value 1 to be a reference value or an indicator, in this case, to verify if there could be any difference or not between the two population variances or between the two standard deviations. Thus, in this task 3.11, we can verify that there could be no difference by saying that the 90% confidence interval does contain a value of 1 which indicates that the two population variances or the two population standard deviations could be equal with a 90% level of confidence. Before ending this session, let us do a checklist on the achievement of this topic's learning objectives. After watching this video and learning the techniques on estimating the ratio of two unknown population variances, denoted by sigma 1 squared over sigma 2 squared, and the ratio of two population standard deviations, denoted by sigma 1 over sigma 2, are you now able to obtain or calculate the point estimates for sigma 1 squared over sigma 2 squared and for sigma 1 over sigma 2, which is the first learning objectives of this topic? Please recall that the point estimate for these ratios are the ratios of sample variances or sample standard deviations respectively, which you can obtain from sample data or sample information. What about the second learning objective? Are you now able to construct a confidence interval for sigma 1 squared over sigma 2 squared and for sigma 1 over sigma 2? Remember, we only have one case in constructing the confidence interval in this topic, where we only need to use F-scores in the confidence interval formula. No Z-score, no T-score, neither a chi-square score. It is only F-score in this topic. Two important assumptions underlying this topic are: first, the data are assumed to be normally distributed, and second, the two populations are assumed to be independent. Finally, are you now able to interpret the constructed confidence interval for the ratio of unknown population variances or for the ratio of unknown population standard deviations? Remember, the indicator value is 1, not 0 this time, unlike in the case of a difference between two means or between two proportions. Check if the confidence interval for the ratios contain the indicator value of 1 or not in order to verify if a difference between the population variances or between the population standard deviations could exist or not. Finally, by ending this session, we are at the end of Chapter 3 on estimation. Please have a look and try out more questions on all 6 topics under estimation chapter to get a real good grip on this chapter. Please do not hesitate to contact me via email or WhatsApp if you have any queries related to this chapter. Until then, Assalamualaikum and thank you very much for watching. All the best, guys.